right, 3, 2, 1. Hello, everybody, and welcome back to the Data on Kubernetes community. Always excited to be here. We are here for live stream number 128. That's right, we're making killer progress. And speaking of progress, things are coming up quickly. We've got KubeCon on the horizon. You're going to have the full schedule for KubeCon coming out very, very soon. I promise, if not today, tomorrow. And if not tomorrow, very, very soon after that, we're going to be having over 30 talks and panels in one day. So a lot of relevant DoK content. Mark your calendars for May 16th at 9 a.m. Europe time, Central European time. That's about midnight if you're on the West Coast, like our guest today. But like I said, definitely check that out. Before we get started, something we've kind of we haven't mentioned as much in some of our other live streams is our wonderful sponsors. All right, so we've got a very nice group of sponsors here. I just want to give a quick shout out. If you haven't checked them out, you can check them out also on our website. If you want to get to know them better, they're always, folks are always asking and answering questions in our Slack. Massive shout out to our sponsors for all their support. If you're interested in sponsoring, just let us know. We're easy to find. We've got an email for that on the website. Also, you can contact me on Slack. That being said, all right, we are in live stream number 128. We've touched a lot of topics, all right? We've touched a lot of topics. Talked about databases, we've talked about storage, we've talked about operators, talked about operators a little bit more. We've gone here, we've gone there. Today, we're going to be touching on the topic of Apache Druid, right? An intro to Apache Druid with none other than my newly acquired friend, Sergio Ferragut, who joins us today from Temecula, California. Sergio, how you doing?
Good, how are you?
Very, very good. Very nice to have you with us. So, Sergio, can you tell us a little bit about your job at Imply and how you got in touch with Kubernetes?
Well, my job at Imply is a developer advocate. I promote the open source project of Apache Druid and help people adopt Apache Druid in multiple forums by answering questions and getting people to actually use it in a performant way. Kubernetes, I've done a little bit of Kubernetes in the past in previous jobs, so I had a little bit of experience. So when I got here to Imply, one of my first tasks was to get the Helm chart that is part of the project and get it functional and test it out and then talk about it. And so that's what this presentation is.
Perfect. Well, with that being said, folks, as usual, you can ask questions here in YouTube. If we don't have enough time to get all the questions handled, we can take the conversation to Slack. Sergio, that being said, if you want to start sharing your screen, you can go for it.
Let me start that out.
All right.
You should be seeing the presentation at this point.
Perfect.
All right. Well, again, thank you. You already did an intro, so I won't introduce myself again, but thank you for having us. What we're going to talk about today is an overview of what Apache Druid is. So the fact that it's a database and what its architecture is and what it's good for. And then we'll go a little bit into an overview of Kubernetes and Helm charts as, just what they are. And then how the Apache Druid project, the Helm chart in the Apache Druid project can be used to deploy and to reconfigure or to upgrade the Apache Druid database in the deployment. So, and then we'll talk a little bit about what it doesn't do, right? Or what the Helm chart still doesn't have, and the fact that this is a community project and we're inviting all of you who are developers and want to improve, test out the database, and who want to help us improve it, to help jump in and improve the Helm chart, because particularly in this group, I imagine there's folks who understand Kubernetes and Helm charts better than I do. So we want to invite you to participate. So with that, let's start with what it is, right? So Druid is a database. It can scale in and out and up and down in terms of storage, in terms of query capability, and in terms of ingestion throughput. It can bring in data in real time and in batches. It can perform on-demand aggregations and does really speedy ingestion to reduce latency from the occurrence of an event to it being queryable and in analytics. So to give you a better flavor of what that produces, right? It produces something we call immediate intelligence, right? Which is applications such as this one that you're seeing here. And let me click through to get the other videos. There should be more videos there. Hold on.
All good. No worries. Perfect.
There we go. The other video. So these are videos of the use of an application that is developed on top of Apache Druid database. These videos are not accelerated at all. They're real-time videos, and you can see the speed with which you can slice and dice the data. And this is the database responding with that speed. So that's what we're doing, right? We're doing real-time intelligence on events that are coming in with the context of historic data that can allow this kind of interactive experience in analytics. So the developers, wanted to build this kind of application, the original engineering team, and so they tested out a bunch of different technologies in order to build that experience, that interactive experience, and they failed with many different databases, but they took certain elements from different kinds of engines to build this new engine. So from the log search software, we took the flexible schema, the real-time ingestion, and text search capabilities. From time series databases, we took the time as the primary display and filtering and grouping dimension, time-based partitioning of the data and storage, time functions, and this ability to do fast ingestion. And from columnar databases, we took the efficient storage format, right, and the speedy statistical computation, resilient data management that we can get out of columnar databases. So with those characteristics, they designed a new database that created this ability that actually works. It provides ingestion that can scale to millions of events per second, proven. The query engine that provides aggregate results with sub-second response times, and a data format that is both storage and compute efficient, and that can give a unified view of not just real-time data, real-time events and analytics, but also with the historical context, because it has both the historical data and the real-time data within within its storage, and is designed to query all of that time frame, all of those time frames with sub-second response times. So let's talk a little bit about the architecture now. So the database is made up of a series of microservices, right, that we can group logically into three categories. The first one on the left, query services, provide graphical user interface, REST API into all of the functions that the database provides, the query resolution itself, and high availability and scalability of the query services. The data services is where data ingestion occurs. For both streaming and batch. There's data indexing going on. This is the building of those columnar data structures that are all indexed and compressed, that are used then for historical. And again, highly available and scalable. And we'll get into a little more details of how it provides that high availability. And finally, the master services, which are the controllers, right? That they're controlling the ingestion. They distribute tasks to the data services in order to achieve the ingestion. They do data management, which is the distribution of data across the cluster, and the high availability of that data within the cluster. There's a fourth category that's not intrinsically part of the database services, but it's a dependency, and that's something we call deep storage. Now, deep storage is where these columnar segment files that we're building during ingestion, that's where we store them, and it's a durable storage mechanism, which can be distributed file system like HDFS. It can be S3, GCP, or Azure, and it can even be used locally, but that only works if you're doing just a standalone on a laptop. So, you can build from a laptop database that's just running for test and development to a 1,000-node cluster. That's the biggest one that I know of. That's a massive capabilities of ingestion and query. So let's talk about the different processes that are involved in the database, right? The first part is data ingestion, right? And it uses a subset of these services to do data ingestion. There's the router where the user submits ingestion requests, the overlord process, which manages batch and streaming jobs, and the middle managers that actually do the job in parallel. So the way this works is the It starts at the router. The user uses either the UI or submits ingestion request through an API. And the router, as its name says, routes the request to the appropriate service, right? The router can route any of the requests to across the services of the cluster. In this case, in ingestion, it routes it to the overlord, and the overlord takes over the job, defines what tasks need to be executed, and distributes the tasks among the middle managers. That's another point. Well, it also, as it distributes the task, it monitors the task, so it knows whether when they complete or their progress, and if they fail, it does the restart of a task if it needs to in a different middle manager, if there was a failure in a middle manager or anything like that. So it provides resiliency of the ingestion job itself. For streaming, it actually enables a special kind of task, which is called a supervisor task, which itself generates tasks in an ongoing fashion to continue the ingestion process from streaming technologies. So, so during ingestion, the middle managers, once they get the tasks assigned by the overlord, the middle managers do what they're told, right? They consume the data from the data sources, whether it's a batch source or a streaming source. They create segments, so that their job is to ingest data, create these segment files that are this specialized Apache Druid format that is optimized, partitioned in time, and potentially partitioned along other dimensions. It is a columnar structure that is compressed and indexed. All of the dimensions are automatically indexed. And once they complete these segments, they push them into deep storage. And as they are consuming the data in real-time streams, they also provide query services. So that's what gives us the real-time access to the data. So you have these middle managers consuming data from streams, and as queries come in, and we'll get into the query in a bit, but as queries come in, they respond to queries on the data that's being processed to build segments. So we get the real-time aspect of it, and then we'll talk about the historical part in a second. The other part of middle managers is that they can scale, and they can scale pretty dynamically, right? So as the ingestion volume grows, if there's fluctuations in the flow of events in a stream, the middle managers can scale. We can add more middle managers, and the overlord will assign more tasks to those middle managers to do more ingestion in parallel, right? And therefore increasing the ingestion throughput that it's capable of. Let's go to the next one. So now the data management side. So we've talked about ingestion. There's these middle managers creating segment files and pushing them off to deep storage, publishing them. That's where the coordinator process comes in. The coordinator recognizes new segments as they're published to deep storage, and it makes decisions about where to distribute them among the historical processes. The historical processes are the ones that will respond to queries on historical segments, on ones that are no longer being processed in real time. So it distributes them, not just each segment in one historical, but also replicas across different historicals in order to provide high availability and resiliency, such that if you lose a historical, that same segment of data is available from another historical to continue querying the querying capability. So now query processing. So we've talked about ingestion, right? The data coming in either through batch or real-time streaming. It produces segments, puts them in deep storage. The coordinator asks the historicals to load segments so that the segments are locally available within each historical. And so when the query side comes in, the router again receives a query request either through the user interface, the graphical user interface, or through REST API, either in SQL or in JSON native query language that Druid has. It takes the request and routes it to the brokers. There could be many brokers, and that provides more high concurrency and more processing power, because the brokers are also involved in resolving the queries. So they take the request, they split it up into individual tasks that they need to send either to the middle managers if it's a real-time portion of, so if the time frame of the query is within the real-time portion of the data, or to the corresponding historicals for the time frames that it knows the historicals have. So it uses this metadata about where the data is distributed to send the tasks to the middle managers in the historicals that need to process that query. Each one of them process a part of the query, reading the segments that they have locally or in memory, in the case of the middle manager, produce results that are then merged within the broker, and where final calculations may occur to merge or to do group buys and that sort of thing across all of the data that's been gathered, or all the results that's been gathered from the cluster, and then return those results back to the client. So that's the overview of the three major functions that Druid has: its ingestion, its data management, and its query. Right. So now let's talk a little bit about Kubernetes. I'm going to speed through this a little bit because there's we don't have that much time, and you guys probably know this better than I do. But this is the story of where we started, right? I don't know, 30 years ago or so or more, we were deploying directly on hardware, right? We had hardware that had a specific operating system, and we deployed apps on top of that operating system and managed all of that manually, which was quite a task. When we went to virtualized deployment, right? We started adding hypervisor on top of the operating system and created virtual machines that themselves had an operating system. It had all the binary dependencies of the applications and applications themselves. This helped a lot because it allowed us much better configuration management. We could create VM images to deploy rather than having to deal directly with the hardware that we had before. Then this evolved further into container deployment, right? Where containers are more lightweight than VMs, right? The containers don't have an operating system of their own. They use the host operating system to deliver operating system functions. So they're more lightweight. They only contain the binaries that are their own dependencies for specific applications. And this allows us to do easier configuration management and deployment. So what does Kubernetes provide? Kubernetes provides the management of these containers, the deployment and configuration and orchestration is the word that's used normally for what Kubernetes does. So it it acquires and manages nodes, the hardware or the VMs that it's going to run stuff on. It deploys containers into them, and it accepts and deploys requests, object requests, which is, there's many different kinds of objects in Kubernetes that you guys probably know better than I do. But it instantiates the containers, it monitors the application status, and it does so from the perspective of an application or a service, right? So it manages the restartability, the fault tolerance, and the upgrade strategy of services that are made up of sets of containers or sets of pods. In Apache Druid terms, you can use Kubernetes to deploy multiple clusters of different characteristics. In this slide, we have a couple of examples where we have a single node deployment where all of the services are in the single node, and this would be probably a test dev deployment where high availability is not important. Or you could have a larger cluster with many nodes that deploy services across nodes for high availability and manage those services across nodes to provide a full, highly available platform for Druid. So why Apache Druid on Kubernetes? So we've sort of been mentioning this, high availability is a big deal. And it provides, because Kubernetes is monitoring and then restarting components as it needs to, it provides recovery. So it has this monitoring and restart capability of the pods where appropriate. It has functionality like anti-affinity. This allows us to make sure that if there's a set of pods that provide a given service, you don't ever have two running on the same node, because that would that would cause a point of failure if that node fails. That actually causes failure of the functionality of querying and so forth. So anti-affinity helps us actually provide high availability and creates only no single point of failure situation. It also allows us to do scalability, right? You can manage individual components by changing the scale of a component either manually to increase the capacity of a particular service to, for example, increase the number of historicals or increase the number of middle managers. And it also does so automatically in some cases. And in the Druid case, the auto-scaling functionality is really useful for the middle managers in order to increase and decrease according to the ingestion workload that there is. And we'll talk about how, that's probably the only place where we can do auto-scaling, but manual scaling we can do anywhere. It also provides security, it provides encryption of communications, the ingress control and network isolation. And finally, it manages the upgrades. So we can do rolling upgrades automatically by creating certain rules within Kubernetes as to how the upgrade process evolves. So now let's talk a little bit about Helm charts, because we can do, we can deploy on directly on Kubernetes by creating these large definitions, these YAML files where we define all of the services and all of the elements manually, or we can use a Helm chart. A Helm chart provides, harnesses this complexity by creating templates for each of the services. And we'll talk a little bit about how the templates are built for Druid. And it uses a file structure that describes component templates, their parameters, and it provides this single set of parameters from which you can just adjust parameters to deploy very different configurations of Apache Druid in this case. It also has dependencies. In this case, the Apache Druid Helm chart uses Zookeeper, and it uses a metadata database. Internally, in this case, it deploys either Postgres or MySQL as the metadata database. And it provides, again, this values, that YAML file that has all of the defaults of the parameters, and in which you can change the parameters, only the parameters that you need to for the deployment that you want to do. So as an example, you can create this historical with a replica count of 10 and the middle manager with a replica count of 6. And those are the only two parameters that we can change that we can change to deploy a cluster that has 6 middle managers and 10 historicals as the scale of that deployment. It's not as easy as that, but that will work. You can generate a cluster that is that size with all of the other default parameters. You'll probably want to change other things as we'll discuss in a moment. So let me move to the next one. So let's dive into the Helm chart, right, and what it contains for each of the services. So first, all of the query services, the router, the broker, as well as the master services like the overlord and the coordinator, use similar configurations in the Helm chart for Kubernetes objects. They include a deployment, which defines the stateless set of pods that will monitor them and keep them running. An ingress, which controls access from outside. In that case, the only one that really requires access from outside the cluster is the router, because as we've mentioned, the router is the one that distributes requests to all of the other services. So the router is the one that usually has the ingress enabled. All of the other services can keep the ingress disabled because all the other communication is internal. And finally, the service definition that declares and manages a set of pods as a logical network service. So now to the middle managers. In the middle managers, the template defines a stateful set, which is different than the deployment, in that the middle managers hold intermediate processing files locally. So that makes it stateful. And therefore, when it restarts, we want it to come back with that storage in place. If the storage itself fails for some reason, it can come back and rebuild from scratch its tasks. But having it come back with its intermediate files in place allows us to pick up the jobs where they left off. So it also defines a pod disruption budget. This is how we upgrade. So what is essentially defines is how many pods can be offline while we're doing the upgrade. In the case of Druid, it depends on how many replicas you've used, but typically you're using replicas of the tasks, replicas of the segments in the cluster. Typically it's 2, so that means we can only lose 1 pod at a time during an upgrade process. You could increase that to 3, and you could lose 2 at a time during the upgrade, but normally it's configured with 2 replicas and 1 pod down at a time for upgrade. The service, again, defines the set of pods as a logical group. So the middle managers define a service. Because it's as a service, it has, a logical network identity and a port that's consistent that we can communicate with. And finally, the horizontal pod autoscaler, the HPA, which can be enabled to control autoscaling of the middle managers, right? Where you define a minimum number of pods for that service, maximum number of pods, and then you define metrics and thresholds that will trigger the increase or the decrease of the number of the replica count of this service, and therefore allow it to grow and decrease as the workload changes. The historicals also use a stateful set. And this is where the Kubernetes actually provides very quick recovery times, right? And recovery points. Because remember, the historicals are loading from deep storage. They're taking segments that are immutable, right, and loading them into their local, what's called their local cache, essentially their local storage. Which is usually SSDs for if you want to have it be faster. You can have different historical tiers that are, faster or slower, but we won't get into the tiers for now. So the historical keeps copies of the segment files locally, right? And so upon a restart, if a historical fails, if during the restart they have the files, then they don't need to do anything else. They're back in service almost immediately. The pod disruption budget, same as the middle manager, we control it one at a time. Again, it depends on the replicas of the data source. So if their segments are replicated twice, you can lose one historical at a time to do the upgrade. Segments are loaded and unloaded from local storage as the historical. So if you're scaling it up or scaling it down, when you scale it up, the coordinator recognizes the new historicals and decides to do a redistribution of the segment files, and therefore unload some of the segment files from existing historicals and loads them into the new historicals, and therefore increases the query capability of the historical layer. That process of redistribution does take some time. So this is why we don't recommend using the HPA in this case. Because we don't want it to scale automatically. If it's scaling up and down automatically, there's going to be a lot of overhead of redistributing the segments that you probably don't want to be occurring in an automatic fashion. So scaling historicals is probably better done manually. So let's walk through an example. The first thing we need to do is set the Kubernetes context, right? I've been experimenting with Minikube, doing it on the laptop. I'll actually share a link at the end to a blog post where we'll go through from scratch into how to build a Minikube Apache Druid deployment on your laptop, on a Mac. Anyway, so you set the Kubernetes context either on Minikube or Amazon EKS or Google GKE or Azure AKS or any Kubernetes cluster deployment, right? You clone, from scratch, you clone the Apache Druid repo, and then run the Helm dependency update. What this does is it downloads the Helm charts for Zookeeper, Postgres, and MySQL, so that you can deploy them from your Kubernetes context. And finally, the last command, the Helm install, will actually install and deploy a whole Kubernetes cluster within the whole Apache Druid cluster within the Kubernetes context. So that's the simplest model where you get 3 zookeepers for quorum. You get 1 historical, 1 middle manager, 1 broker, and one master service that's a combined coordinator and overlord. So that's the simplest configuration. And from there, you can change parameters to make it bigger. So let's take a look at an example of how you would manually use the Helm chart to update or to change the deployment of this particular Apache Druid deployment. So the best practice is, well, you make the change that you want. So at the top there, we see a simple values file that's only changing the historical replica count to 2. So we started with 1, we're going to 2. By using a Helm diff upgrade command, we can see what the change is, and it's a good practice to do this before you actually deploy it, but to see what you're changing from the already deployed cluster. So here it shows us that it was replica count 1, and it's going to replica count 2. Once you do that and do the Helm upgrade command, that will reconfigure the cluster. So it tells Kubernetes, okay, take historicals from 1 to 2, and it will do that. We see here in the get pods command that we've added. We had historical 0, we'd added historical 1, and I caught it right as after the upgrade command, so it's not yet ready, but it becomes ready within a few seconds actually, and then the coordinator starts its redistribution of the segments across the two historicals now. So let's get into the Helm chart and the different parameters that are needed to deploy this. So for deep storage. Let me get the first animation there. So for deep storage, we need to define the storage type. Like we said, we need to figure out whether it's going to be S3 or HDFS. And this is any S3 compatible environment. Actually, in the local deployment, we're using min.io to deploy, and you configure it as S3. And there's a series of parameters that are needed depending on which deep storage you're using, things like the access key to access S3 and so forth. And this link that I provide here, it gives you all of the details of what those parameters are. The metadata database also needs to be configured, right? By default, it'll use a Postgres instance, but you can define something different for that metadata database if you have some other database that you want to use that's not necessarily that instance of it. So the Helm chart provides either PostgreSQL or MySQL. But there's one thing here that's missing from a high availability perspective, and this is one of those things that we probably need to improve from the Helm chart, and that is that the metadata databases that it's deploying are not highly available themselves. So because of that, there is a point of failure here that still needs to be improved on. So let me see, my animations are messed up there, so let me go to the next one. Now, within all of the other microservices, right? There's a section of within the values.yaml file that defines for each service what the resources are. And this becomes important in larger deployments where you want to provide more CPU and more memory to each of the pods that make up the middle managers, or that make up the brokers, or that make up the historical. So it's important to look at these at the resource requests and at the limits that you're assigning to each of the services, according to the set of nodes that you have and the capabilities in terms of resources, CPU and memory that are available. But this is definitely something that needs to be adjusted when you're deploying a larger cluster. And a very good resource for figuring out how much CPU, how much memory you want to assign to each one is this link that I provide here, the basic cluster tuning that's part of the Apache Druid documentation. It provides a lot of details as to how you want to configure it, how many you want to configure. So more gives you parallelism and gives you high availability, but each one needs to have a certain amount of CPU and memory to efficiently do their jobs. So let's take a look at it from a data processing perspective again. So each of the processes that we talked about, right? So from a data ingestion perspective, we want the router to also be highly available, right? So if it fails, we want another one available to provide that same function. So we probably want a replica count of 2 in the router at a minimum. And this is where we do want to enable the ingress. So those are primary parameters that need to be changed in a larger cluster. Now in the overlord and the coordinator, you also want a replica count of 2 because these are the master controlling services that handle the ingestion jobs and the data management jobs. So you want them to be highly available as well. So replica count of 2 on those 2 is highly desirable as well. On the middle managers, the parameters are, again, the replica count, a minimum of 2 for high availability, but you really want more, right? Well, it depends on your workload. If it's just a test environment, then 2 is probably enough. But anyway, this is where you manage the scale of the ingestion capability and of the real-time query capability. You'll want to set the anti-affinity in order to avoid 2 middle managers being on the same physical node. And you could also use the node selector. So if you have different kinds of nodes for different services, you can direct the middle managers to potentially the more powerful nodes where there's more CPU, more memory, because this is one of the real workhorses of the Druid implementation. Let me see what else. Okay, so during data ingestion, right? It's not just having multiple middle managers for failover capabilities, but it's also so that the flow of data itself is not interrupted. Right, so you can use within an ingestion job. Let's talk about the real-time ingestion job in this case. You'll want to have replicas of the tasks themselves. So this is the same task, the one that's let's say consuming from a Kafka topic or consuming from a subset of partitions of a Kafka topic. You want each task to have a replica of the task, and it's 2 tasks doing the same work. They're ingesting the same events and they're producing the same segment files, such that if there's a failure of one of the middle managers for any reason, the other one continues to work and continues to provide that real-time query capability on the data as it's coming in, and you don't have interruptions and have to restart a particular set of events to reprocess. It will restart that if you don't use a replica count, so it will restart from wherever it started before to build a segment. But because there's a real-time query capability going on here, if you don't have the replicas, what that would cause is if you have just a single task doing the ingestion and it fails, it'll restart from the beginning, and any queries that are coming in that might have been further along a few minutes ago and reported a sum or an average or whatever metric that was higher because it had already processed a bunch of events, it might go back to less events because it's reprocessing, and therefore provide results that seem to go up and down. So by having replica tasks, you avoid that problem and provide real high availability to the ingestion process. As the task, if you have the 2 tasks doing the same thing, you obviously don't want the results from both. The overload automatically takes care of that, and as one finishes and completes and publishes its segment, it stops the other task that was the replica doing the same work. So anyway, that's sort of how it provides the high availability of ingestion. So I sort of already talked about the ingestion capacity, but so the scaling the ingestion capacity. Okay, so scaling it can be done manually, right? So you just increase the replica count of the middle managers to increase both its throughput and its ingestion throughput and its query capability and its concurrency for more queries on the real-time aspect of it in a static way. Or like we said before, you can use the autoscaling capability, which is enabled within the few set of parameters in the values.yaml. You just enable the autoscaling, define minimum and maximum replicas, and define the metrics and the thresholds that are used to either increase the replica count or decrease the replica count based on the current workload. On the historicals, again, we'll want 2 minimum for fault tolerance. You'll also want to use a node selector to choose the specific nodes on which you want historicals to run. You'll want to use anti-affinity again, so that if a node fails, you don't actually have a failure. There's another historical to take over. And now when you scale up, right? So if you increase the replica count, the coordinator will recognize the new historicals, redistribute the segments, unloading the segments from one historical and loading it into others. The historicals are deployed as a stateful set. So this means that the naming of the historical persists and the storage persists. And this is one of the huge advantages of putting Druid on Kubernetes, because because of this, there's no need to reload segments, right? If you didn't have this capability, you say you lose a node and there's no persistent storage on it, and you bring back another node with the historical, it'll have to retrieve all of the segments that it had from deep storage. And it does that, and that works, but that creates a larger delay in the recovery capability. So from this perspective, the Kubernetes capabilities of a stateful set is a huge advantage for the Apache Druid database. On the broker side, so brokers, like I said, are, yes, you want more than one for fault tolerance, but there's also scale, right? And there's two scale, you want to scale them up enough to deal with individual queries that they may have. So this requires, more threads for more concurrency. It requires more processing buffers to do merge operations of the results and enable higher concurrency just by having more resources. Now, scaling out is also very useful by increasing the replica count, again, for higher concurrency, but also for high availability and an ability to direct traffic. So you can create rules that send different kinds of requests to different brokers. And so you can create sort of fast lanes for faster queries and potentially slower lanes for more harder workloads. So it allows you to do that kind of query leaning. So let's talk about possible failure scenarios during query capability, during query processing, right? So if you're processing a query and a middle manager is lost, like I said before, the replica tasks keep the real-time queries consistent. So you'll want to have replica tasks. Upon recovery of a middle manager, it'll be assigned tasks and continue working by picking up where it left off and just continuing its ingestion and its query capabilities. If a historical is lost, because you've set replica count of the data segments to 2, the replicas are available in different historical. So if it's halfway through processing a piece of a query and it fails, the broker recognizes that and resubmits that particular task to the other historical that has the same data. Upon recovery, like we said, the historicals recover really fast with Kubernetes because they have the segment cache already populated locally, and therefore can pick up right where they left off and start receiving more queries when they come back online. If a broker is lost, the query that was submitted will need to be resubmitted because it was in charge of that particular query. But recovery is fast because the persistent storage. Sorry, this is the wrong point. Another broker will take the request, right? While that broker comes back. But the other thing about Kubernetes is it will bring that broker back. So your query throughput capability, your concurrency capability will be recovered fairly quickly. So even if local storage, I probably already mentioned this, but if local storage is lost within a historical, if there's a failure in the storage, the queries will continue with the other replicas. And as the new historical is brought back and given new storage, it will then retrieve the segments that were assigned to it from deep storage and recover from there. In the meantime, there's other historicals taking care of those queries. So summarizing, the Apache Druid is a real-time OLAP database to produce the kind of applications that I showed you an example of. Kubernetes gives it increased availability by monitoring it, by doing auto recovery and providing persistent storage. This gives us better recovery times and better recovery points. And it auto-scales the ingestion components and the real-time query capability based on the workload. And the Helm install makes it really easy, right? So once you've defined the set of parameters that you want for a particular kind of deployment, you can save that as a values file, like the few examples I have here, like a dev with a min cluster, a QA with HA enabled, and maybe a production cluster that has not just HA enabled, but the auto scaling capability enabled. And deploying a new one is really just a Helm install with this values file, and off you go. So what doesn't it do yet, right? The Helm chart doesn't have all of the capabilities of the Apache Druid database enabled at this point. And one of those things is metrics. So the database is fully instrumented, and you can enable metrics for each of the services that provide all sorts of detailed metrics at the query level, at the segment level, at information about CPU utilization, memory utilization. All of the resources are monitored and reported on a continuous basis when you enable metrics. This is really useful for understanding your workload, understanding how your workload is evolving, where it's hitting problems, where you may need to change the configuration and do a Helm upgrade to provide the additional resources that you need, or maybe reduce the resources if you're using too many and you don't need that much. So metrics is something that we would like to add to the Helm chart. A multi-tier configuration. So this is the ability to do the historicals can be configured on different nodes. So you can have a set of historicals that may be on really fast, lots of CPU, lots of memory, and all SSDs to provide maybe the time frame for the last week, or so it's time based, right? So you may have those the last week of data in the really fast hardware, and then have older data migrate to slower hardware, where you might have, maybe less memory, less CPU, less hard drives instead of SSDs. That gives you the price performance combination that you want. So the multi-tier configuration of the Apache Druid is not a part of the Helm chart at this point. So that's an improvement that we're looking for the community to build. And finally, this is a community, and it's an active open source project with lots of engineers working on it from lots of different organizations. And we want more. We want this community to grow. Right? We want the project to become even more active. So given that you guys are all Kubernetes knowledgeable, I want to invite all of you to test it out. Fork the repo, make changes to the Helm chart, add some functionality to the Helm chart, and submit a PR. We're reviewing PRs and merging PRs almost continuously. So with that, I'll leave you with a lot of different ways of communicating with us. There's email, there's the Druid user forum, there's Slack, there's meetups like this one. There's a training program that for now is completely free. So I invite you to go to learn.imply.io and learn more about the basics. There's a Druid basics course that just walks you through the basics of how to ingest data, transform it, and query it. There's a more advanced course on modeling and ingestion that takes it further in terms of how you need to model your data to make it really performant and deliver the kind of interactive experience that we showed in those videos. So go to the training site and take advantage of what is currently free courses. And there's the Druid Professionals group, the news on Twitter. You can, if you follow us on Twitter, you'll see new blog posts and new information that we have all the time about events and about how Druid is evolving. So with that, I'll open it up to questions.
Very, very good. Superb presentation. As I said when we got started, we've had 128 live streams, and few have been as fluid and as well organized as this one. Just really, really nicely put together in terms of the logic behind everything. One question that someone was asking me on Slack is, as someone with a fair amount of experience, such as yourself, and we're talking about cloud native, et cetera, when first approaching this, in your personal experience, like you showed us, how to get Druid onto Kubernetes. What was the trickiest part for you, though? And if you had to do it all over again, what might be some resources that you might recommend, or things that, in my case, I wish I'd known a little bit more about this or about that, or things that folks should watch out for?
I spent a lot of time trying to figure out the ingress side of it, but that's my inexperience with Kubernetes more than anything else. And I suddenly realized I could just use the kubectl port forward to enable it in my case. So let me find the link. I'll share the blog post where I go through actually deploying.
Oh, perfect. Yeah. Definitely find that
on the laptop. I want to follow it up with another blog post where we're deploying a larger cluster on AWS or on one of the cloud services. So that, that's where I assume I'm going to get into a little more trouble.
No, like you said, it's good. And the thing is, because Kubernetes presents different things that perhaps aren't as familiar, such as ingress, and also for some people getting used to Helm charts and YAML. Like there's a whole stack of things to be dealing with. So yeah, no, if you can share the link to that, that'd be really, really good.
Absolutely. Let me find it and I'll share it here in the chat in a second.
Yeah. And then another question is regarding standardization of practice. Like you mentioned, some of the things that are going on in the Apache Druid community, very exciting stuff there with different contributions that are making these things easier. Having seen other technologies go through the process of standardization of practice. Oh, good. I got the link right here. What are things that you think that, us as a community or things that you're noticing that will help what we often talk about for data on Kubernetes to become more boring, and in the sense of not so not as overwhelming as it might be for some people, and have a more sort of like, this is a straightforward approach, this is how it's done?
Well, like I said, I'm no big expert on Kubernetes, but what I found is that the Helm chart was just a godsend, right? It was very easy to take the Helm chart and just to figure out which parameters I wanted to change to deploy a whole cluster. So from that perspective, that was enlightening to me. The Helm charts were new to me at that point. They're still kind of new to me. So the Helm chart was something that I found was phenomenal. These, like I said, the abilities of Kubernetes to provide higher availability than the database by itself could provide was also, I think, a huge benefit in my mind to deploying on Kubernetes rather than on some other structure, like directly on EC2 or directly on hardware. Got it.
No, very, very good. Another question that we got from the audience, from Renato, is what's your opinion about using the Helm versus Druid operator?
Not much opinion in my mind, because I know of the Druid operator. I have not experimented with it. That's also another task that I want to take on, right? To figure out, under which situations the Druid operator might be better. Actually, you guys may be able to tell me which one would naturally be better. From a newbie's perspective, the Helm chart seemed easier as an initial point for me. I don't know. The Druid operator, I assume, has more functionality, right? Because there's functions that the operator itself provides, as far as I can understand it. I'm not, again, no expert.
That's okay. And when it comes to operators, it's a common topic that comes up a lot, because without having more standardized practices or deeper integrations with Kubernetes, operators for right now kind of seem like the best option we've got. And so, like I said, that is a frequent topic of conversation. Renato, I invite you to come into our Slack. We've got plenty of other people that would be happy to take that.
Talk about it. Yeah.
Yeah. Got another comment. Just they love your presentation and very well configured explanations. So yeah, great feedback there. I think that's I'll give folks a little bit more time to drop their questions in there. But Sergio, if you can stop sharing your screen really quickly.
Absolutely.
So I can share mine. Perfect. Good. So while you're talking, tradition that we have in the Data on Kubernetes community, I think we started this in probably live stream number 10, if I have to go way back when, to the ancient times of 2020. It seems like it's been 50 years, but we have an amazing artist, Angel, who's in the background doing a graphic recording of all the stuff that you're talking about. So we have that right here. It's sort of a unique thing that we do, but it's a nice way to compile all the different things that were talked about, as you covered a lot of ground. You covered a ton of ground in a short period of time. So very, very well done there. Like I said, I think, it's very clear if folks want to check out, Druid more, get in the community, and you already know somebody through Sergio. So if you need a little bit of help here or there, you know who to go to. And I like I said, I haven't seen very many presentations that have been as thorough and easy to follow. So we have a very grateful audience. You're getting more shout outs to you as well too for the amazing presentation.
That is awesome.
Yeah. That being said, we've got you in our Slack. If anybody has any additional questions, we're happy to continue the conversation there.
Absolutely.
And I hope to see you in the Bay Area in July when I'll be back. We're doing more in-person meetups, folks. If you're in London, if you're in Bangalore, if you're in Istanbul, we're going to start opening these up more in more countries. I'll be doing one in Spain at some point as well, too. And anyway, Sergio, thank you so much for your time today.
Thank you.
All right. Take care, everybody. Cheers.